Hello guys, welcome to our YouTube channel. So today we're going to look at Physics 2022 Northwest Mock Paper 1. So let's dive right into it. Question 1 says, which of the following is correct? So we'll just go through the answers and then we decide which are not correct. So A says, a non-homogeneous equation may be physically correct. Well, if it's not homogeneous, then it must be physically incorrect. So when you say may be physically correct, it means that it has a possibility of it being correct, which is not true, right? So whenever it's not homogeneous, it's always not correct. B says a homogeneous equation must be physically incorrect. Well, if you took this may here and put it here, right, this guy would have been true because a homogeneous equation may be physically incorrect. But now the problem here is it says it must be physically incorrect, and it's not true because homogeneity just tells you the possibility of a particular physical equation being correct, right? So it must not be incorrect. C says a non-homogeneous equation must be physically incorrect. Well, if it's not homogeneous, then it must be incorrect, right? Because homogeneity is the necessary condition for the correctness of a physical equation. Whenever a particular physical equation is not homogeneous, therefore that is a sufficient condition that that physical equation is incorrect, right? All right. That's what C is saying there. Then D says that a homogeneous equation must be physically correct. Well, if it's homogeneous, then it must not be physically correct because it's possible that it's homogeneous and then yet still incorrect, right? And you know why: presence of dimensionless constants, logarithmic expressions, and all of that. Perfect. So let's go to the next. So the answer is actually C. Alright, so our question 2 says, if a stone tied to a string is whirled to move in a vertical circle at a constant speed v, then... Alright, so I just want to head over to draw the motion of a particle in a vertical plane here, and then we'll look at the dynamics of that motion. Now, I've just drawn an arbitrary situation here. The particle is at x, and then we want to resolve, right? We want to study the dynamics of that motion, really, at this point x. So we want to resolve all the forces that are acting on the particle at x. So you have the weight that is like here. So we have to resolve this weight into its components. So the component that is parallel to this plane, to the plane of the string, is basically mg cos theta, and perpendicular is mg sin theta. So what we want to do is, since the centripetal force is actually the resultant force that acts on particles that are whirled in a circular path, right? So the centripetal force is always towards the center, so we're going to take the resultant force towards the center. So we'll take this T minus mg cos theta equals the centripetal force. So that's why I've said at x here. So we have T minus mg cos theta equals to the centripetal force. Now, what happens if you bring this thing at C? So let's look at what happens at C. Now, if this string gets down at C, this theta becomes 0. So if I put 0 here, you basically realize that cos 0 is 1. So we have equation T minus mg equals to the centripetal force, which means that our T is this plus that. Now, what happens if we go over to B? If we come over to B here, so if you are whirling that particle and it gets over to B, you realize now that the angle subtended by this string from the vertical is 90. So you could put your 90 here. Cos 90 is basically just 0, so you have T just equals to the centripetal force. So at B here, the centripetal force provided solely by the tensional force. Then we can go over and then study the dynamics of the motion at A. So at A, you realize that now there are two forces acting towards the center, the T and the mg. So both of these forces will sum up to provide the centripetal force. So you realize that we'll have T plus mg there equals m omega squared r. But again, if you want to study why it's like that, you basically come back here at your theta. When it has revolved from C all the way to A, your theta now is 180. So you put 180 here, because 180 is just -1. You multiply that, so you have T plus mg cos theta equals that. That's why you have T plus mg cos mg this equals that. So your T now is that. So again, you can just look at this generic form of analyzing the motion of a particle in a circular path, which is in a vertical plane. So you can study the equation of this generic equation, and then you deduce every other particular equation for every portion or for every point the particle is in this path. So you realize that in June 2021, that's the physics paper 1, question 24 had to do with this. Since most teachers teach in high school and then they just basically study the motion of the particle at C, B, and A, those are the common positions. So some teachers never really get to talk about when it's at a particular point like that. So that was a question in physics paper 1 2021 GCE last year. All right, so you realize that we can form a relationship between their tensions, the tension here and here and here. So because the tension here at C is the biggest because you're adding these two terms, at B you just have one of those terms, and then at A, you rather have the difference of those terms. So the biggest tension is at C, so that's why I've said TC is greater than TB is greater than TA. So which means that your answer here is just A, because it says the string is most likely to break when the stone is vertically below the center of the circle. Correct, because that's where the tension is greatest. But again, let's just discuss why B, C, and D are wrong. B says the tension in the string is maximum when the stone is vertically above the center. Of course, that's not true, because when it's here, the tension is rather minimum at A here. C says the sense of the acceleration changes with direction of the velocity. That's not true, because the acceleration is always directed towards the center. In fact, that's how you define simple harmonic motion, right? So it's the oscillatory motion. It's an oscillatory motion, right, for which the force acting on a particular particle is directly proportional to its displacement and is always acting towards the equilibrium position. So the acceleration always has a particular direction, which is towards this equilibrium position. So that C there makes no sense. D says if the string breaks, the stone will continue to move in a circular path. That's not true. If the string breaks, the stone continues to move in a path described by the velocity, right? So the velocity is tangential like this to the path. So the particle would simply move in this particular direction like that. Good. So we go on to the next question. All right. So the next part of the question says the amount of energy needed to convert 1.2 kilogram of pure water at 60 degrees Celsius to steam under standard atmospheric pressure in joules is. All right. What we want to do here is that, of course, since you are getting water, for it to become steam, you have to get it from you have to get the water from 60 degrees Celsius all the way to water at 100 degrees Celsius. Now that's the boiling point of water. So the water now has to boil off, right, and then become steam. So we first of all need an enthalpy. So we need a particular energy that would supply to that system to get the water from 60 degrees Celsius to 100 degrees Celsius. That's that energy. Now the energy that you require to break the bond so that the gaseous molecules that are leaving are absolutely free to leave that particular system, thermodynamic system, you'll be supplying, of course, a heat that is associated with the specific latent heat of vaporization of water, right? So that's why you have this term here. So you just basically, substitute MC, the theta, and then MS, LVS. So the latent heat of vaporization of steam is basically 2.26 times 10 to the power 6 joule per kilogram. So you put in all of that, you have your answer as this. So our answer is C. That was easy peasy, lemon squeezy. Okay, so we are on question 4. For a moving core metal to function properly, the pointer needs to make a swing and then rapidly return to the equilibrium position. The kind of damping necessary to achieve this is. All right, so very quickly, well, devices that work on that require pointers to make measurements, you really want your pointer to return back to the equilibrium position as quickly as possible, right? So so that the device is ready to get the second measurement, or if you are getting the measurement twice, you want it to get back very quickly to equilibrium position when you remove the weight or perhaps whatever thing you're measuring, so that you can get the second measurement. So the kind of damping you'll be required for that kind of system will be critical damping. Now, critical damping is just the kind of damping you get for oscillatory systems, such that a displaced particle gets back to the equilibrium position within the shortest possible time. That system is said to be critically damped. But if it's heavily damped, then you realize that it takes all the time in the world to get back to the equilibrium position. Now, what you have to note is that for critically damped and overly damped systems, those particles don't overshoot the equilibrium position, so they just move from a particular displacement back to the equilibrium. They don't have all the energy to go and move and overshoot the equilibrium position and then coming back like your simple pendulum. So your simple pendulum overshoots the equilibrium position and then back and overshoots and then back, overshoots and then back. So that's really just like damping, right? Because over time you realize that the amplitude of oscillation of your simple pendulum dies out to 0, so it eventually comes to rest. So that's what is indicated here with this red graph. So that's a lightly damped system. For critical damp and heavily damped, you have indicated another diagram here, but the critical damping comes to 0 very quickly. So you want that for your measuring instruments, right? So you studied this in electronics a bit when you talk about signal attenuation, and even in waves, because you get to talk about attenuation a bit in waves. So lightly damped systems, all right, so they experience attenuation basically. All right, so we move on. The answer is B, right? So we get the answer as B. We move on to the next question. All right, so the next question is question 5. The net force acting on the object R in figure. So, okay, so we just want to talk about net force here. But very first, you realize that there's a force to the right, there's a force to the left. So the resultant force, since the force to the left is bigger than the force to the right, the resultant force will be to the left here. All right, the resultant horizontal force will be to the left, and then the resultant vertical force will just be downward. So the resultant force on this system will basically be in this direction like that. So what direction is that? If this guy is west and this guy is south, so this is southwest, the resultant force will be southwest. So either A or D, correct? Right? So but we have to calculate and see then and choose between A and D which one is correct. But you have already eliminated B and D. B and C, they can never be correct. So you just get the resultant vertical force is that guy pointing downwards, so it's negative. So the resultant horizontal force, this guy is negative to the left, and this guy to the right is positive. And then you get that the resultant force. Then you get that the resultant force is 60 newtons. So A is our right answer. Question 6, that an electric field consists of a region between two plates separated by a distance d across which a pdv is maintained. The work done by the electric field to accelerate a charge of 3e through a distance of 2x in the field is, okay, I'll just draw a small diagram here. So this is our electric field, right? These are the plates. So this is the distance between the plates, a voltage v. Then you have this charge particle, then you have to move it through a small distance 2x. So the very first thing you want to do is that, okay, of course the work done to move it like that is force times the displacement. Now, but the force in this electric field is what? Is the electric field strength times the charge on the charge, right? Because this charge is moving through this electric field, so the force on it is basically this. So but electric field strength is the potential between these plates divided by d. Now it's just because this is a uniform field. So the plates between the area between the region between the plates of a capacitor provides a uniform field. You have to take note of that. That's a passage question. So V over D times Q times S. So you realize that, but what is our Q? The charge on the particle is just 3e. The S, the distance the particle moves, is 2x. So we multiply all of those together. We have 6evx over D. So our answer is A. Question 7. The magnitude of the force between 2 point charges maintained a distance r apart is F. If each of the charges is doubled and their separation apart increased to 3r, the force between them becomes, okay, so generally the force between two charges is given like that. That's Coulomb's law. So we can go on and say, okay, the force, the new force now, so we call it Fn, that's a new force. So the charges now, it's just doubled, right? So Q1 becomes 2Q1, Q2 becomes 2Q2, and then the distance between them increases to 3r. So you want to now have 3r squared there. So if you multiply out these things and you simplify, you have that. So you factor out this 4 over 9, you're left with k Q1 over Q1 Q2 over r squared. So this force like that is basically this F. So realize that our new force is 4 over 9 times F. So our answer is C. Question 8 says, a ball is thrown vertically into air with an initial velocity u. The time it takes to return to the point of projection is, well, that's basically time of flight, because if you project something vertically, right, it gets back to that same point where you projected it. You can basically use the equations of projectiles to get that. So time of flight is 2u sine theta over g. So we have that, our theta there, because the angle of projection from the horizontal is basically 90, because you are projecting it vertically upwards. So you have sine 90 there, so your time is simply 2u over g. So your answer is D. All right, question 9 says a mass attached to a vertical string is made to undergo simple harmonic motion. Which of the statement below is correct? All right, before I get into the statements, let's just study the motion of a particle that's oscillating in simple harmonic motion a bit. So we have, okay, let's just assume that the particle begins to oscillate from rest, right? So the displacement equation would simply be r sine omega t. So you can get the velocity of the particle by differentiating displacement. So the rate of change of displacement velocity. So we have to differentiate this guy. We have omega r equals omega t. So we can go on to get the acceleration by differentiating this guy again. So we have negative omega squared r sine omega t. But then you realize this r sine omega t is x. So we have our acceleration to be negative omega squared x. Now you realize that the acceleration of a particular particle that's oscillating in simple harmonic motion is always proportional to what? To its displacement from the equilibrium position. But then the problem is the acceleration always acts towards the equilibrium position, but the displacement increases away from the equilibrium position. That's why you have this negative sign there. Good. So we have the first fact that we have established. We can go on to talk about the kinetic energy, because I think amongst the answers you will talk about the kinetic energy and potential energy. So we are just having a brief rundown. So the kinetic energy of that system is half mv squared, like every other system. So we have half m. Now in place of this v, remember that our v here is omega r equals omega t, so you put that here, you square that, you have this. Then our potential energy is half kx squared. Of course, we all know that. So we have half, our k is m omega squared. Our x is our x here, so we put it in here, we square, we get this. So if we add those two guys, if we add the kinetic energy to the potential energy, it gives us the mechanical energy. You realize that we would simply have this guy and this guy, will factor them out, because we have half m omega squared r squared, half m omega squared r squared. So you basically factor them out, and then you get cos squared theta plus sin squared theta, which gives you 1. So when you add those two guys up, you have this particular constant. You realize that the mechanical energy does not vary with time, because there's no time in this particular equation for mechanical energy. So any answer that talks about the mechanical energy varying with time is a wrong answer. So let's just go. The direction of its acceleration is constantly changing. That's not true, because we have established here that the direction of the acceleration is always towards the fixed position, the equilibrium position. B says that when its P is increasing, its KE is reducing, and vice versa. Well, that's very true, right? Because you have the sine and cosine curves here. But again, I'm just going to demonstrate it over here. That B is correct, but let's just see why C and D are wrong. The total mechanical energy of the system varies sinusoidally. Okay, that's not true, right? So it's not sinusoidal, it needs variation, because again, the mechanical energy is just a constant like this. Then D says the closer the mass is to the equilibrium position, the greater its acceleration. That's not true. The acceleration is greater when the mass is further away from the equilibrium position. That's when the displacement is biggest. Correct. So I'm just going to draw the graph over here. So that's the P and the KE of that system. Then this is the E total. So they've asked this in June 2012, right, for students to be able to draw this. So I'm just drawing it because I'm answering other questions for you. So perfect. So the PE is 0 at equilibrium, right? And then the kinetic energy is maximum, and it varies like that, right, with a 90 degrees phase difference between them. The total energy is just constant. That's why you have E total here, you have negative E total here, right? All right. So normally this guy is not supposed to be continuous like this, right? But again, because if you well, it's all right. It's all right. We'll just continue. Okay. So yeah, our answer is B. Question 10 says the colors of light blue, yellow, violet, orange in order of increasing wavelength is. All right, so you know about Röykbeef, right? So this Röykbeef, red, orange, yellow, green, blue, indigo, violet, it's actually in the order of decreasing wavelength. So if I start from violet all the way to red, that will be in the order of increasing wavelength. So but again, you can also talk about this order being the order of increasing energy. So the color of light that has the greatest energy is violet. The one that has the greatest the next, all right, after that greatest energy, the next energy, biggest energy, will be indigo, and then the next blue, and then the next green, and so on. So you realize that the guy with the biggest wavelength is arrow here. All right, so that's the wavelength order there. So but if you arrange it from red all the way to violet, that will be in order of increasing energy, because the violet is the guy with the most energy, right? Because the frequency is highest. So the guy with the highest frequency is the guy with the most energy. Then if you arrange from violet, indigo, blue, green, like I've arranged, that will be in the order of increasing wavelength. Again, this is an important question. It came in FET 2020, and it has come in many GCE questions. So just take note of that. So our answer is D. So we go to the next. The next question says that a radioisotope has a half-life of that, and an initial activity of that counts per second. Its activity after 2.5 hours in counts per second is. All right, so let's get the activity after this time. So the T half, we just want to write that in seconds, and then the initial activity is that. Our total time is 2.5 hours. Sorry, it's not 2 hours, it's 2.5 hours, but I've corrected it here. So we have 2.5 times 60 times 60 in seconds, so that's 9,000 seconds. So there are two equations that I usually tell students to use whenever they are dealing with radioactivity. It would give you, I think, 90% of the solution you require. So T equals NT half, right? The total time of decay is equals to N, right, times T half. So we make our N there. N is just an integer. N is just the number of interval decay. So you talk about the time taken for it to drop to half its original value, then the time for that half value to drop to its half, which is a quarter at the time. So N is those number of intervals that you get. You understand now? So we have our N there is 25 on 6, which is not exactly an integer, but that's okay. In high school, we can go ahead with that. So our A0, the next equation will be A0 over AN to be 2 to the power N. These two equations, you always use them and you always give your answers in radioactivity. So our A0, we make our AN the subject. So our AN will basically be A0 over 2 to the power N. Our A0 is the original activity, which is 1600, our 2 to the power N. So you basically take this and you put it there. So our answer is 100.2 counts per second, which is A. So the reading of the voltmeter in the circuit in figure 2 below is, so we have this answer. So what we really want to do here is that you have to realize that if this is VA, if I move from A, so I'll have VA, right? Now the current flows into this 4 ohm resistor. So I have VA plus the voltage across this guy. Then I come all the way like this minus the voltage across this guy to be equals to VB, right? So that's a conservation. So since the electric field is a conservative field, we can basically, the work done in the circular part like that is basically 0. So if I took VA all the way and then added this guy, right, I would simply have equal to 0. Then I've just, what I said, if you sum all of that guy, it would give you the potential of this guy. That's the statement of the law of conservation of energy. So we realize that our VA minus VB, so I can just rearrange this equation so that I have VA minus VB equals V5 minus V4. Now, but we have to get the potential across the 5 ohm resistor, right? So again, you realize this 5 and this 3, they are basically in series because we are assuming that this voltmeter is a perfect voltmeter, so no current goes through it. So if no current goes through this guy, it means that the current comes here, it splits. Current gets into this guy. The current that gets into the 4 ohm resistor is the same current that goes into the 6 ohm. The one that goes into the 5 ohm is the same current that goes into this man. So you realize that the 4 and the 6 are in series, the 5 and the 3 are in series if this guy is a perfect voltmeter. So the voltage across the 5 ohm, we will just use the potential divider rule. We have 5 over 5 plus 3 times the PD, the EMF that's applied to these two guys, which is 18. Then the voltage across the 4, again, you do the same thing. You have 7.2. Then to get VA minus VB, which will be what our voltmeter would read, will simply be this guy V5, which is this, minus V4, which is this. So we have 4.1 there. So our answer is D. We have a beam of green light causes the emission of photoelectrons when used to illuminate a metal surface. If the metal surface were illuminated with red light whose intensity is greater than that of the green light, the observation will be, all right, so there are two things you have changed. First, you've changed the color of light that's being used. Now you are using red light. Now the truth is red light has a lower energy compared to green light. So if it's having a lower energy and then there's still photoelectricity, so there are still photoelectrons ejected from the photosensitive surface, you realize that the kinetic energy of the photoelectrons will now be lower because the energy of the incident radiation is now lower, right, according to this equation. So the energy of the incident radiation, subtract the work function of the metal there, all right, which is again basically the surface potential of that photosensitive cell surface. So it will be equal to the kinetic energy of the photoelectron. So you realize that if I'm reducing the energy here, the energy of the incident radiation, by using color of light that has a longer wavelength and a shorter frequency, you realize that the kinetic energy reduces. And because the kinetic energy reduces, the stopping potential also reduces, because the stopping potential then is just the negative potential on the collector plate, right, for which 0 amperes of photoelectricity flows through the circuit, right? All right, or you say 0 amperes of current as a result of photoelectricity flows through the circuit, correct? So again, this guy is, so that stopping potential reduces. All right, so the right answer here, again, stopping potential has to decrease, so this guy decreases, this guy decreases. So the answer is either A or D. So let's go to the next part. So because the energy has reduced, but then what have you done? You have increased the intensity. So if you have increased the intensity, it means that the number of photons that are hitting that metal surface per unit time has increased. So the number of photoelectrons that are ejected per unit time has increased. It means that the current, all right, the photo current, all right, the photoelectric current has actually also increased. So you realize that your answer to photoelectric current has actually increased. So A is our answer. Perfect. Here we go. A capacitor of capacitance 120 microfarad is charged by a 9.0 volt battery through a resistor of that, the time taken for the capacitor to acquire of 75% of its final charge in seconds is, okay, we're charging up the capacitor, so we'll use the equation for charging a capacitor. Q equals Q naught 1 minus e to the negative t over RC. So what we want to realize here is that, of course, the charge at that particular time is 75% Q naught. So you realize, because Q naught is the charge when it is fully charged, right? So you have 75% Q naught basically is 0.75 Q naught equals Q naught, all of that. So we can basically divide all through by Q naught, and then we make this guy the subject. So we have this. So if we make negative t over RC the subject by taking ln on both sides, you have this. So our time now becomes negative RC ln that, but ln of that again is this answer. So you substitute, and then time is 13.3 seconds. So our answer is C. All right, so the final question for our series today would be, when washing tomatoes in water of density this, it is found that a particular fruit float such that only 15% of its volume is above the water. The density of the fruit in kilogram per meter cube is, all right, so let's go. So let's say that the density of water is rho W, and then the volume of the object is just V, all right? So the volume of the object in water will be 0.85 V, because remember that if 15% of it is above the water, it means that 85% of that particular substance or object is inside the water. So the volume of the object in water will be 0.85 V. Now we want to find the density of the object, so we don't know that. So, but then what you have to realize is that the force, right, the force the object exerts on water is equal to the force the water exerts on the object. So that's why the object comes in equilibrium at that particular point where 15% of its volume is above the water. So we want to get what's the force that the object exerts on the water. So it's just the density of the object as relation to gravity times the volume of the object. Now, if it's equal to the force that the water exerts on the object, then you want to get the density of the water, right, times as relation to gravity multiplied by the volume of the fluid that is displaced. Now, the volume of the fluid that is displaced is simply equal to the volume of the object that is within the fluid. All right, that's fully immersed within the fluid, and it's 85% of that object that is immersed within the fluid. So we'll just go ahead and then first of all make our rho O the subject, because we are looking for the density of the object. Then we go ahead and we say, so in place of our rho omega, which is density of water, we just put our 1000 kilogram per meter cube. This G cancels with this G, then V. So the volume of the object within water, so again, is 0.85 V, all that over V. So our density is 850 kilogram per meter cube. So our answer is C. Thank you guys for watching. If you enjoyed this video, please like, comment, subscribe, share it to your friends. If you want us to do more work and any other maybe suggestion you have, please leave in the comment section below. Thank you so much for watching. Stay fine. Thank you.